I'd like to say hello and thank organizers, reviewers, and all the participants of the UI 2020. In this talk, I'm going to summarize the paper Neural Likelihoods via Cumulative Distribution Functions, which was co-authored by Professor Ricardo Silva and myself, Pawel Chilinski, part-time PhD student. We leverage neural networks as universal approximators of monotonic functions to build a parameterization of CDFs by the application of automatic differentiation with respect to response variables and then to parameters of the CDF representation. We are able to build black box distribution and density estimators. The main motivation behind our work include a direct evaluation of tail area probabilities and coherent estimation of low-dimensional marginals of a joint distribution without the requirement of fitting a full joint. A suite of families is introduced. We evaluate different representations empirically on a variety of tasks. The structure of MONDE, monotonic neural density estimator for univariate responses, is sketched in figure. Covariates and response variable are root nodes. We use sigmoid in the output unit T representing conditional distribution. To guarantee that T represents a valid CDF, we must enforce three constraints. We choose the following design to meet these conditions. Constraint: every parameter that multiplies output of a node that is descendant of a response variable to be non-negative. They are represented as squiggled edges. The rest of the parameters are unconstrained. This guarantees monotonicity condition 3. Additionally, due to the range of logistic function being 0, 1, first and second constraints are also guaranteed to some extent. We can use an automatic differentiation to generate the density function f. Once the PDF is constructed, automatic differentiation is invoked once again, now with respect to parameters, to generate gradients to be plugged into any gradient-based optimization algorithm. A standard way of composing multivariate models is to use a copula, which is a multivariate distribution function with uniform marginals. Copula allows us to individually model marginals and the dependent structure. Here we use Gaussian copula, combining the univariate MONDE models f1, fk. The density function is shown in the equation and its computational graph in the figure. The individual marginal distributions are transformed via standard normal quantile function phi inverse. Correlation matrix can be estimated as the low-rank factorization of the covariance parameterized by the covariate vector. The estimated marginals and correlation matrix are combined with zero-mean Gaussian density phi rho. Our final model is a flexible multivariate CDF parameterization, PUMONT, pure monotonic density estimator. It is combined with differentiation with respect to multiple response variables to provide a likelihood function. The graph representing a monotone function with respect to each response variable with no finite upper bound is presented in figure shown. Each dashed rectangle represents a function. Hx transforms the covariates. Hxyk is a monotonic with respect to yk. M is element-wise multiplication of all its inputs. T is a monotonic with respect to all its inputs and return a positive real valued scalar. In this model, hidden units uses softplus if it has more than one response variable ancestor and sigmoid otherwise, to guarantee that mixed derivatives are greater than or equal to 0. The density is then computed from the transformations as shown in the equation. By plugging in 1 as input of the T transformation, we normalize the output to represent a valid CDF. In the next few slides, we describe experiments in which we compare our and baseline models on various tasks. In the table, we show results on density estimation using UCA datasets, average test likelihoods, the error bars of 2 standard deviations. Our suite of models is represented by the MONDE MADE, which is autoregressive MADE, which performance is shown in the last row of table. It matches the performance of NAF model for the power dataset and exceeds its performance for the gas dataset. We achieved slightly worse results on the other UCA datasets, but we noticed that our model had a tendency to overfit the training data in these cases. Here we compare CompuMonde and PMonde models to baseline classifiers, neural network, random forest, XGB on a problem of detection events falling in the tail of the distribution. We use financial data from which we construct 3-dimensional response and 21-dimensional covariate. We want to assess the model's ability to correctly rank tail events of three assets experiencing loss at least 95 percentile of their historical value. To do this, we obtain the 95 percentile for each dimension of the y from the training set from which we compute the labels. The test code for the trained estimator is computed by feeding it with covariate and 95th response variable percentile. Such computed ranks and the true labels are used to compute the ROC and PR curves. The discriminative methods are trained directly on labels predefined before training. Our estimators do not have to use partial thresholds at the test time. It can be changed after training is completed, which is not possible for discriminative models. Pawel and neural network classifier obtained noticeably better results. In this experiment, we use our and baseline models to estimate a measure of extreme dependence between two random variables. We generate synthetic data for the experiments as mixture of two conditional components. Both components have covariates generated from Gaussian with different means. The response variable of first component is Gaussian, which has no tail dependence, and the second component is sampled from t-distribution, which has non-zero tail dependence. We plot tail dependence coefficients as u changes from 0,5 to 0 and 1. The tail dependence behavior exhibits itself when such curve tends to value greater than 0, when u approaches 0, 1. We present our concentration plots, one for each mixture component. The second one, which depicts concentration plot for t-distributed component, clearly represents tail dependence. We can see that only Pawel and math models are able to capture fatted tails in data. In many practical problems, we are interested in estimating only partial marginals. We test the ability of our models to encode coherent bivariate dependence in the data for problems of large dimensionality. We use financial data as described already in the tail event classification experiment, but with 21-dimensional response and 21-dimensional covariate. To assess model performance, we compute the average log likelihood for each bivariate combination of response variables, giving 210 unique pairs. Each cell of a table contains the number of times the average log likelihood computed for each bivariate combination of response variables was larger for model shown in the row compared to the model shown in the column. We can see that the best performing model on this test is Pawel, which has obtained larger test log likelihood in all 210 cases. We propose a new family of methods for representing probability distributions based on deep networks. Our method stands out from other neural probability estimators by encoding directly the CDF. This complements other methods for problems where CDF representation is particularly helpful, as computing tail area probabilities and computing small dimensional marginals. As future work, we want to exploit its relationship to graphical models for CDF. Thank you for taking your time to listen to this presentation.